Okay, we're going to continue our discussion of whatever 29.3 was, Lenz's law. We've been talking about Faraday's law and Lenz's law and how we can use electromagnetic induction to make electricity. We're going to start, we're kind of in the middle of a section, we're just going to start with some examples. An example 29.3 is basically about a type of generator, and it's basically a simple alternator. And it looks like this. We've got a magnetic field. Here's my magnetic field. And in that magnetic field, we need some type of loop or coil of wire. I'm just going to draw, here's sort of an imaginary axis or an axis. We're going to have this loop of wire that rotates. It's going to rotate about that with some angular speed. I'm not going to draw the connections and explain the finer points of how you make a generator, but we basically have this disc that's spinning. Well, because it's spinning, the amount of flux that goes through that disc is continuously changing, right? So when it's perpendicular, you get a lot of flux. When it's parallel, you don't get any flux, and most of the time you're somewhere in between. It says that our magnetic field is uniform. The loop rotates about the axis, and as a result, the magnetic flux is changing. We know that if we have magnetic flux that's changing, that's going through the loop and it's changing, it's going to induce an EMF. So that's kind of our result here, is that we get this induced EMF. If we set it up so that at t equals 0, the position of the angle is 0, like so we're going to start at a 0 position at t equals 0, and we have a constant omega, then the position at any time would just be omega t, where omega is that angular velocity. However fast it's spinning, its position will just be omega t. The flux, of course, is B times A times cosine phi, which is B times A times cosine omega t. If we take the derivative, we can find the induced EMF, right? So I know that the induced EMF is the negative of the derivative with respect to time. Let's think about this. The magnitude of B is constant and the magnitude of A is constant, so they just come right out. It's this part, it's the angle part that's changing with time. What is the derivative of cosine?
It's just sine, well, negative sine.
It's negative sine, so we're going to get negative sine omega t, but we have to do a chain rule, times omega. So when we do that, we can see that the induced EMF is going to be positive. We're going to get omega B A sine omega t. That's not going to be a constant EMF because we've got this changing angle all the time. If we graphed that, it looks something like this. Let's say it's an alternator, so it produces an alternating current or an alternating EMF. This is the flux equation here. Well, really here. If I were to graph that as a function of t, the flux, it would look like a cosine wave. It would start with its maximum at 0. That's probably not a perfect looking graph. That's the flux. If I want to graph the EMF, I'll do that in blue. The EMF is actually going to be out of phase. It's going to have its maximum values right here, and it looks like this. So this would be the EMF. If you think about that rectangular coil of wire, you can think about what it looks like. Right here where you have maximum, the coil would be oriented like this. Right here where it's 0, the coil would be like this. Right here where it's minimum, it's just negative, it still looks like this though, right? It's just the other way. And you can kind of picture, and of course in between it's spinning, so it looks like this. It's hard to draw all that in. Anyway, but that's what's happening. As that coil rotates, the amount of flux changes, and as a result we get this induced EMF that looks like that. I don't think there's anything on the homework that makes you use these formulas, but I just kind of wanted you to see it's really not that hard to get an equation that describes the flux. Magnetic field area, cosine of the angle, but if it's moving with an angular velocity, that's just omega t. And then it's really not that hard to take a derivative and get an expression for that induced EMF. That's one type, and I don't know that you'll see it again. This other one kind of comes up a lot. Even though it's not nearly as practical as this alternator. Not as practical, but it's easy to get some homework problems. It's easy to use. Okay, I'm still recording. Good deal. I don't want to lose David. This is example 29.5, and it's a slide wire generator. Now the slide wire generator looks exactly like the rail gun. It's the same idea. We have this conductor here. We have a magnetic field that's directed into the plane of the board, so magnetic field. And it's supposed to be uniform no matter how it looks when I draw it. Doesn't look too bad. So there's magnetic field into the board. We've got this loop, and we've got a conducting bar. I'm going to put the bar right here. But it's going to have a velocity so that it's moving to the right. So it's not going to stay there. if we stop and think, as we pull it to the right, the flux changes because the area changes. If you increase the area, the amount of flux that's flowing through that loop is going to get bigger. So we can see that. At some later time, it's going to be here. I'm going to come back and we're going to think about this. But if we're moving to the right, this distance right here from here to here, it's just going to be the velocity times the time. So we think about that. How long did it take? That's what we're going to be looking at. That's that distance right from here to here. All right, let's do a little thinking about how it's going to work. We know that B is into the page. We also know that the area is increasing. So that means that the flux is increasing into the page. We have more and more flux passing through. If we stop and think about that, if the magnetic field and the magnetic flux is into the page and it's getting stronger, what direction is the induced magnetic field going to be? Or Jordan's the only one here to answer a question, and he's writing. I don't want to lose you. I want us to think about that. If the magnetic field is into the page, so that the flux is into the page and increasing, what direction is the induced magnetic field?
Would it be the same?
Now, remember, the induced magnetic field opposes the change. So if I have more flux going into the board, the induced flux needs to be out of the board. So what I find is the induced B is out of the board or out of the page. If the induced B, I take my right hand, is out of the page, I can see that the current is going to be, and the induced EMF are both going to be counterclockwise. So the induced EMF and current is counterclockwise. I think I said clockwise, but I meant counter. I just put my thumb out of the board and rotate, and I can see that's going to make a counterclockwise current. There is another way I can get that result. That'll give me the exact same thing. I can think about a small positive charge right here. I made that look crooked. So here's my little bar, and right here I have a little positive charge, right? And if I said, what's the direction of force on that positive charge? I would put my fingers with B. I'd turn into the magnetic field, and I can see that that gives me a force up, and that's going to cause counterclockwise also. So either way I do it, I get the same result. I can just say, what's the direction on one single charge? Velocity, V cross B makes that charge go up. And of course, it'll just make this path. All right, same thing with Lenz's law. I get counterclockwise. Okay, so far so good. Let's see if we can figure out the magnetic field is constant, but what's the area of the loop? In other words, initially it's this big, later it's this big. Well, actually, let's just get the change in the area of the loop. If the area increases from this big to this big, I just need to know the length which they tell me this distance from here to here is L, I can see that the change in area is just equal to the length times, and then that change in that width is just VT. That tells me how much the area is changing, or an expression for the area. The induced EMF is negative flux times the time. That would be B times A times cosine phi. B is constant. Cosine phi is just 1. So we really just need to know how the area is changing with respect to time. That's just going to be negative d dt BLVT, or negative BLV. If we're just interested in the size of the induced EMF, which is usually all we want, we usually write it like this, BLV. That's going to be the size of our induced EMF. If this velocity is constant, we get a constant EMF, which means we get direct current. For a constant velocity, this will just be a constant. I mean, L is constant. Everything will be constant. We'll just get direct current. It's not a practical generator. That alternator that I showed you a minute ago is much more practical, but this one's kind of fun. Anyway, I don't want to leave the picture, but I think we're going to look at some other aspects. Suppose that our slide wire generator that we just looked at has a resistance R. So whether I don't think they necessarily added in a resistor, but they're just saying the resistance of that loop at a particular time is R. They want us to find two things. One is they want us to find the rate energy is dissipated. That's another way of saying the rate that the energy is being used. What is another word for the rate of using energy or the rate of dissipating energy? It's probably David's turn to answer the question. The rate we use energy is called the power. They're basically just asking for the power without saying the word power. Remember, power is in joules per second or watts. So when you're talking about using energy, you're talking about how many joules per second are you using. For a resistor, the amount dissipated is given by I squared R. We need an expression for I. That would just be E over R. times R. You want to play around with that? But we calculated just a minute ago that E was BLV, times R, not equals R. There we go. I squared over R, so BLV, lowercase v, it's velocity, not over R, squared, times R. We don't have any numbers, so we're just getting, that's going to be B squared, L squared, V squared for velocity. And then R squared times R is just going to leave one R in the denominator. So that would be an expression for the amount of energy dissipated by it. If we had numbers, we'd just plug those in. The work done moving the wire so this is not the work done moving the wire. I don't know what this is. The other way we could have done it was with our other approach where we said that you can use power equals force times velocity. In this case, the force would be the magnetic force. That would be ILB times V I have no idea. My notes don't make any sense. I'm going to stop right here because I just work it another way to get the same answer. So it's not really very interesting. So it's creating more confusion. Okay. That's our two generator problems. This next section is going to remind you a lot of this slide wire generator problem. It's kind of a different way to think about the same thing. This section is about motional EMF. If I start with a magnetic field, nice uniform magnetic field, and it's directed into the board. And I have a piece of conductor, a metal rod like that, has length L. Looks just like what we had a minute ago, except I don't have the rails for it anymore. I just have the little conducting rod without the rails. And I'm going to do what I just said now. If I pull this to this direction, if I pull it to the right with some velocity v, what I'm going to notice is any of the negative charges, because it's really negative charges that move. If I have a little negative charge right here, and I use the direction of force, this is a moving charge in a magnetic field. So if I have a negative charge and it's going to the right, and I curl my fingers in, a positive charge would feel a force up. So my negative charge feels a force down. Well, the free electrons then tend to get down here. So I get a negative charge buildup, which means this end becomes positively charged, which means I now have a potential difference between the two ends. very much like I would have if I had a battery where I had a positive terminal and a negative terminal. So I can think about this as A, this is side B. The free charges continue to move until the electric field, because they're going to have an electric field in here now. You know, electric field points from positive towards negative. So I'm going to have positive charge would feel a downward force from the electric field, and they feel an upward force because of the magnetic forces, right? So they're going to continue to move until the electric field E in the rod causes the electric force to equal the magnetic force. Now, I can't say the electric field equals the magnetic field because they have different units and they don't even point in opposite directions. But the magnetic force on these charges pointed that way on a positive charge. And an electric force will point this way on a positive charge. So once those two forces get equal, it'll stop. That means QV will equal QVB, or they'll stop when V is equal to E over B. Notice this is the little v. That's the how fast. It's not a voltage. We know that electric fields are, though, however, equal to the voltage difference A over B per unit length. So once these charges have accumulated, I'm going to have some potential difference from here to here, some voltage. And then, of course, I have this length, so I know that that electric field in here, that electric field that points down, is just equal to that voltage over L. Or, if I rearrange that, VAB is just equal to the electric field times L. But that electric field, according to this, has to equal V times B. So I get V times B times L. I get that the electric field is the electric potential is VB. That's the induced EMF I came up with in the previous problem. That is called motional EMF. That's the exact same formula we came up with in that slide wire generator for how much induced potential or induced EMF you have. Like I say, this is just V is the speed of the conductor. And of course, L is the length. So if you want to do this and get a bigger induced EMF, it helps if you can go really fast, have a really magnetic field, and have a really long rod, okay? an example with that. Got some more notes. I'm just trying to debate. There is kind of what we call a generalized form, and I think I'll go ahead and write that down, but I do not think it's something we're going to need. This is a very specific form of the induced EMF if we're looking at a rod, the way we are. You can get it by moving pretty much any shape. It doesn't have to be a rod. For example, you might have a magnetic field that points into the board and have some arbitrary loop of current, and this would be a little section of that loop, and this whole loop is moving in some direction V. Like I say, there's a magnetic field into the board. So instead of just having that nice straight rod, you've got some other shape, in which case what you would have to do is you have to acknowledge that we have to work a little infinitesimal, a little piece of the induced EMF would equal V cross B for that little segment. And then you would have to integrate that over that whole loop, and you would get V cross B dot DL. That's basically the general form of motional EMF. This one over here, this very specific one for a rod, I know we'll use more, but we might look at an example that uses that general form. I'm not 100% sure. Now, this only applies to having a moving conductor in a magnetic field like that. If you have a stationary conductor, which is what we've mostly looked at, then you must use what we've been using, which is your induced EMF is simply the negative derivative of the flux. So we haven't really gotten away from that. As long as we're stationary, that's what we use. But you can induce an EMF by moving a conductor in a magnetic field. If you just have a rod, which is the simplest case like what we had a minute ago, then you use VBL. And in this case, when we do the rod, you want to make sure that your rod is perpendicular to the magnetic field and that your velocity is perpendicular to both of them, right? So that so the magnetic field and the velocity and the length of the conductor were all three perpendicular to each other, like an XYZ axis. Okay, so let's do an example. We're going to do an example with a rod. Going back to motional EMF in the slide wire generator. conducting rails. Here's our little rod. I'm going to move it this way. We've got magnetic field. Okay, so in this case, we know that this moving rod right here, our rod right here, that acts like our battery because it's a moving rod in a magnetic field. Its motional EMF is just given by our formula VBL. It's moving, it says, oh, I have to write down all the info. The length of the rod is 10 centimeters, 0.10 meters. It's moving at 2.5 meters per second. The magnetic field is 0.60 Tesla, and the resistance of the loop is about 0.030 ohms. Not very much, just a middle loop. So E is just VBL. So we have 2.5 meters per second, 0.60 Tesla, and the length is 0.10. If we went back and we reviewed what Tesla was and we actually put all this in, it would come out with units of voltage. That is 0.15 volts. That's our induced EMF. Again, if we need to know direction, it's counterclockwise. You can get that by using Lenz's law. You can get that by just saying, hey, let's just look at one little positive charge. What would happen to one little positive charge? The current is just your induced EMF divided by your resistance. And we get current of 5 amps. Okay, think that's good enough for motional EMF. I do have another example that uses the general form, but I don't think I want to work it. I do want to work this next problem, this next section though. Section 29.5 deals with the idea of induced electric fields. We've been talking about induced magnetic fields where if you have flux that's going through a loop and the amount of flux is changing, then you get an induced magnetic field that opposes that change, right? That's what Lenz's law says. If the flux is up and it's increasing so that there's flux going up and you're getting more and more of it, then you induce a magnetic field that points down. You get an induced magnetic field that opposes any change in the pre-existing magnetic field or the flux through a loop. Well, it turns out that anytime you have a changing magnetic field, you're also going to induce an electric field. So let's consider a long, thin solenoid encircled at its center by a conducting loop. Okay, long, thin solenoid looks like this. And we've got wires wrapped around this. So something like this. It's a wire that goes around and around. And they're in real life, they're probably very closely spaced. But I can't draw 2,000 loops, so I just draw a few. And finally, there you go. We've got current going in. We've got a solenoid. It's got this cross-section area that we're going to call A. Right there. I want to put a loop around it. I'm going to put a pretty blue, just one loop of wire going around it. See if I can draw a good loop. But I'm going to insert a galvanometer, G. All a galvanometer is an ammeter. A galvanometer just measures current, but it measures really small current, so it's really sensitive. So the galvanometer is basically just a sensitive ammeter. Galvanometers were pretty much the main thing in old school ammeters and voltmeters. We don't make ammeters and voltmeters anymore that use them, but I still have like some galvanometers. That's what I used when I showed you current the other day in class. Just a real sensitive little meter. All right, let's think about the magnetic field. We have a formula for a long, thin solenoid. The magnetic field at the center is mu naught N times I. If you remember that N is just the number of loops per meter. And that's the formula for the magnetic field of a solenoid at its center. Okay? So our flux that's going through our loop, or let's just say our flux that's coming out of the solenoid is just B times A, which is mu naught N times I times A. So that's all of my flux. I kind of want to look at one thing in the book. Is A supposed to be the area of the solenoid in this case, or is A supposed to be the area of my loop? Let's double check. You guys catch up. Okay, go ahead. I'm going to pause you for just 1 minute, David.